Welcome to Talk 8. Today's topic is agreement and reliability studies, a category of veterinary literature that's becoming increasingly common as new measurement devices, imaging techniques, and observer-scored scales are introduced into practice. You've probably seen papers asking, does this new portable blood pressure monitor agree with the gold standard? Do two radiologists agree on scoring thoracic radiographs? Is this pain scale reliable when used by different nurses in the same clinic? These are agreement and reliability questions, and they require completely different statistical tools from the efficacy and diagnostic tests we've covered in earlier talks. The key tool you'll encounter most is the Bland-Altman plot, and today you'll learn to read one confidently. Let's get into it. Here's our roadmap. We'll work through the three main tools: Bland-Altman plots for comparing two continuous measurement methods, Cohen's Kappa for categorical agreement, and ICC for continuous reliability. The unifying theme is that correlation is not agreement, a point that trips up many readers. Two measurements can be highly correlated and still disagree systematically in a way that matters clinically. We'll see exactly why. Think about why this matters clinically. You see a paper introducing a new oscillometric blood pressure monitor for cats, claiming it correlates well with Doppler systolic BP. You buy it, but 6 months later you notice you're diagnosing a lot more hypertension than before. What happened? The new device might be precise, it gives consistent readings, but it's systematically biased 15 millimeters of mercury higher than Doppler. High correlation doesn't catch this. Only a Bland-Altman analysis does. This distinction between reliability, which is about consistency, and validity, which is about truth, is critical. A scale that always reads 2 kilograms too heavy is perfectly reliable, but not accurate. Both matter for clinical use. Altman plot was introduced in 1986 specifically to address the limitation of using correlation to assess agreement, and now it's the required standard for method comparison studies. Here's how to read one. Each dot is one patient measured by both methods. The x-axis shows how big the measurements are, the average of the two. The y-axis shows how much the two methods disagree for that patient. The central solid line is the bias, the average disagreement. If it's near zero, there's no systematic difference. If it's 15 millimeters of mercury, method A consistently reads 15 millimeters mercury higher than method B. The dashed lines are the limits of agreement. Bias plus or minus 1.96 standard deviations. They tell you that 95% of individual comparisons will fall within this range. The clinical question is, would that range of disagreement matter for patient management? Let's make this concrete. A bias of 2 millimeters mercury between two blood pressure methods, clinically irrelevant. A bias of 20 millimeters mercury, very relevant. You're not measuring the same thing. Limits of agreement of plus or minus 5 millimeters mercury, probably acceptable in most clinical blood pressure contexts. Limits of agreement of plus or minus 35 millimeters mercury, even if the bias is near zero, individual patients can differ by up to 35 millimeters mercury. That's a problem. Fan-shaped scatter is a specific warning sign. The dots spread out at higher values. This tells you the methods agree well for low measurements, but diverge at high ones. For blood pressure, this would mean they agree in normotensive cats, but disagree in hypertensive ones, exactly the population where accurate measurement matters most. The bottom line question is always, given these LOA, could using this new method instead of the reference standard change my clinical decision for an individual patient? Cohen's kappa is for situations where two observers are assigning categorical labels, like grading a lymph node as reactive, suspicious, or malignant, or scoring a radiograph as normal, mild, moderate, or severe. The critical insight is that simple percent agreement is misleading. If you're assigning one of two categories, two raters randomly guessing would agree 50% of the time just by chance. Kappa corrects for this. Kappa of 0.75 means after removing the agreement that would happen by chance, 75% of the remaining possible agreement is actually achieved. The Landis and Koch benchmarks shown in the table on the right are widely used reference points. For most clinical scoring purposes, you want kappa above 0.6 to consider a scale reliably usable across different observers. Weighted kappa is an extension for ordered categories. It gives partial credit for near misses. Scoring a lesion as grade 2 versus grade 3 is penalized less than scoring at grade 1 versus grade 4. Intraclass Correlation Coefficient, ICC, is to continuous measurements what kappa is to categorical ones. It's used when you want to know how reproducible a measurement is, whether across raters, across time, or across instruments. Think of ICC as asking, of all the variability we observe in measurements, how much is due to real differences between patients and how much is just measurement noise? High ICC means most variability is real. The tool is reliably detecting true differences between patients. The two types matter. Agreement ICC includes any systematic bias between raters. Consistency ICC ignores bias and only asks whether raters rank patients in the same order. For clinical use, agreement ICC is usually more relevant. You care about both ranking and absolute values. The SEM is especially useful clinically. If ICC is 0.85 and the SD of the measurements is 10 units, SEM equals 10 times the square root of 1 minus 0.85 equals 3.9 units. Any difference between measurements smaller than about 2 times SEM is likely measurement noise, not a real change. Through this case question together. This one is a trap that many papers fall into. The authors report R equals 0.91 and call it excellent agreement. Let's be more careful. R equals 0.91 means the two methods are highly correlated. When Doppler reads high, the oscillometric device also reads high, but correlation says nothing about whether the actual values agree. You could have R equals 1 with a 30 millimeter mercury systematic bias if every oscillometric reading is exactly 30 millimeters mercury higher. Now look at the Bland-Altman. Bias is plus 8 millimeters mercury. The oscillometric device reads 8 millimeters mercury higher than Doppler on average, already a concern for a cut point of 160 millimeters mercury. But the LOA are negative 14 to plus 30 millimeters mercury. That means for an individual cat, the oscillometric reading could be anywhere from 14 millimeters mercury below to 30 millimeters mercury above the Doppler value. In a cat where you're deciding whether to start antihypertensive therapy, a 44 millimeter mercury range of possible disagreement is clinically unacceptable. The fan-shaped scatter makes things worse. The disagreement grows at higher blood pressure values, which are exactly the values where clinical decisions are being made. The answer? No. This device is not suitable for routine clinical use based on these data. The correlation coefficient is misleading here. The Bland-Altman tells the real story. Key lesson. always look for the Bland-Altman in a method comparison paper. A high R or rho is not sufficient evidence of agreement. Sum it up. Agreement and reliable studies are everywhere in veterinary medicine. Every new piece of diagnostic equipment, every new scoring system, every imaging protocol needs this kind of validation. Your three tools, Bland-Altman for continuous method comparisons, Kappa for categorical inter-rater agreement, and ICC for continuous reliability. For each one, always ask the same underlying question. Is the level of agreement or reliability acceptable for the clinical decision at hand? And never ever accept a correlation coefficient as evidence of agreement. It isn't. Demand the Bland-Altman. If you'd like more short, clear epidemiology lessons, go ahead and subscribe before you head out. And if this video helped, a quick like tells YouTube to share it with other students who might need it. Thanks, and see you next time.